Hello, everybody, and welcome to We Measure the World, a podcast produced by scientists for scientists.
When you think about measuring soil hydraulic properties, people don't always think about soil chemistry or the chemistry of the water that they use.
Right.
And so we had to get our water source from the site that's local, that's best representative of the water that's going into the field. And we also went through a lot of water sometimes. Like we went through, at one point in time, we went through 1,000 gallons in one day doing measurements, which is a lot of water.
That's a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, how scientists are solving research issues, and what tools are helping them better understand measurements across the entire soil-plant-atmosphere continuum. Today's guest, Leo Rivera, operates as a research scientist and director of client success at Meter Group. He earned his undergraduate degree in agriculture systems management at Texas A&M University, where he also got his master's degree in soil science. There, he helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Currently, Leo is the force behind application development in meters hydrology instrumentation, including the HYPROP and WP4C. He also works in R&D to explore new instrumentation for water and nutrient movement in soil. And today he's here to talk to us about his soil infiltration research at Texas A&M University. So Leo, thanks so much for being here.
Thanks, Brad.
You've traveled a long way.
Yeah. I'm excited to be here and talk about some of this stuff that I'm really passionate about.
Great. So we wanted to start off just by giving us a background or a little kind of taste of your background. What got you interested in science in general, and what led you into soil infiltration research?
Yeah, that's a great question. It's funny. I was thinking about this. What really got me interested in science was I actually was taking my intro to soil science at Texas A&M, taught by Dr. Tom Hallmark at the time. And at that time, I was still in ag engineering and ag systems and kind of focused on that. And that class really helped me find something that I actually had a passion for and a love. And it just introduced me to a world I didn't know. And I think most people don't really know soil science is a field you can go into. But that class showed me that. After I got done, I decided, I was like, well, let's dig into this a little bit more. And I decided to take a job as an undergraduate student worker with Christine Morgan. From there, I just really started finding, wow, I love soil science. And it just took me back to a lot of the things that I remembered as a kid, especially growing up in the desert, playing out in the desert, spent a lot of time out on bikes, dirt bikes, just messing around and learning about the soils out there and really just how unique they were. And the desert ecosystem itself is just really cool. You dig down and you see these argillic layers and you're like, oh, wow, what's going on here? What happened? Why is it, why is there this clay down here? And as a kid, I don't really know. But now I've learned so much more about how soils form and all those processes. And then really what got me interested in hydrology and soil physics was actually during this time when I was taking this class, there was a big storm that came through El Paso, a big rain event. The runoff and all the erosion that occurred from that actually wound up eroding the foundation away from a Blockbuster at the time. We're going to go way back. Blockbusters don't exist anymore. But it eroded the foundation away from underneath that Blockbuster, and it actually collapsed inside in the middle. I was sitting there thinking about that. And I was like, that's so cool. Sadly, a building was destroyed. Yeah, exactly. But the process that happens there was just really neat to me. And that's really what got me interested in soil physics. I think just being an inquisitive person, I think science draws a lot of people in because we want to learn more about what happens.
Right.
So,
Yeah. So you get into Texas A&M University. You've moved towards soil science. What were some of the specific research topics that you were working on? What were some of the problems you were interested in solving, and how'd you go about doing that?
Well, fortunately, I got to start out as an undergraduate student worker doing research, which I'm really glad I got to do because it taught me a lot and really helped make me a better researcher anyways, because I got to start early. But the work that we were doing was always focused on soil physics and soil formation and how the two play together. So I spent a lot of time as an undergraduate student worker, actually working in the vertisols of Texas and exploring those shrink-swell soils and trying to learn more about how we can characterize them and then how we can characterize, for example, we were measuring crack formation in these shrink-swell soils, which is really interesting because it completely changes the hydrology of the area when these large cracks open up. So we spent a lot of time trying to measure how can we quantify the amount of cracks that are opening and model that to improve our hydrology models to better account for those cracks that are opening up. I also spent a lot of time helping other grad students at the time do their research. So we were just all over the place doing really fun things, and it was just great to get out in the field. So started with that, and then that kind of evolved into my master's work, which again was focused on those same processes, soil physics and hydrology, and how that all plays together. There's a lot of terms that are thrown around, hydropedology or whatever you want to call it, but it's really just taking those two fields, the pedology and the soil physics, and trying to bring those two worlds together and understand things at a bigger scale.
Right. So as you're going about this, looking at the shrink-swell soils, cracks, infiltration, all that kind of stuff, what were some of the specific measurements that you're looking at to try to answer those questions?
Yeah, that's a great question. I mean, we made so many measurements. When we focused on the work that we did as an undergrad, we were actually out there physically measuring cracks. Wow. And so we had sites that were fenced off, and we would go out weekly, take water content measurements using a neutron probe at the time, which was tons of fun. And then going out and physically measuring how deep a crack was and the width of the crack. Right. And then we were doing that throughout this 1 square meter area. Right. And we did that weekly. And so we had to actually characterize all of the cracks that had formed and try and quantify that crack volume. And so we were comparing that with the water content measurements to build our model. And so that was one way of quantifying hydrology and trying to impact that. That was really some challenging stuff, but it was actually, you learned a lot of really unique things. And then going into my graduate studies, we really wanted to dig more into the impacts of land use and landscape position on soil hydraulic properties. We were measuring things like hydraulic conductivity, of course. So we were using double ring infiltrometers at the time. We were measuring bulk density, because what we're trying to do is take these parameters, so taking hydraulic conductivity, and compare that against things like bulk density. We characterized all of the soils at our sites. We did organic carbon content. We looked at the moisture release curves. We actually ran a device over all of the fields to characterize the variability of the fields, called an EM38 device. So we were just doing a big bulk EC map and characterizing that across the field. And that was really useful because that's actually helped us select where to make all of our measurements. Right. We were comparing, what is actually impacting these bulk EC measurements? There was a lot of things, and I think in any study, there's, you have to make a lot of measurements to really understand what's going on. And so with making a lot of measurements, especially looking at a landscape, you're looking at land use and all these kinds of things, that breeds variability within your measurements. So how did you, I don't want to say overcome variability, but how do you deal with it? How do you mitigate variability within your samples? Spatial variability is probably one of the biggest challenges in field research, especially because there's a lot that can happen. We focused on 3 different fields that were in 3 unique land uses. Fortunately, we had this beautiful USDA station that's been in these same land uses for over 60 years, something like that. So we had native prairie, a conventional tillage field, and then an improved pasture field that was just being grazed. On those fields that are technically the same soil type, these were all Houston black soils. When you run the EM38 device over that and look at the variability, it was huge, even though it's the same soil type. Right. And there's so many factors that impact that. So it's like, okay, well, we've got to characterize all of this variability. And that's really was the fun part, is we were looking at all of these things, trying to figure out, how do we characterize really what's happening across a field and do that with a reasonable error. And so the only way really at the time, and still this is probably the only way to deal with this, is you need to make measurements, and you've got to make a lot of measurements. But you need to know, okay, where is my variability going to come from? Hence why we did the EM38 maps. But you can also look at soil maps and see what those look like, understand your landscape position. And there are natural factors across different landscapes and how the soils form that are going to impact and induce variability. You're going to have wetter spots. You're going to have soil getting translocated due to erosion or just movement below ground of different soil particles. So you have to understand what's going to impact that, and then just try and characterize it to the best of your ability. Right. With all of this going on then, what are some of the broader lessons that you learned or the results of those studies? Yeah, there's a lot that we can go into there, but I think one of the most important lessons I learned, you really need to plan your research project out well. You need to know what measurements you want to take and why. And you want to try and take as many measurements as possible, because it's a lot easier to take the measurements at the time while you're out there than it is afterwards. Right. You're like, I need to go and make this measurement, which happens a lot. And that can postpone graduation. You can push back your finish date for your master's or PhD or whatever it is you're working on. So you need to, kind of just plan things out well and coordinate, talk with the experts in the field. I spent a lot of time talking with my major advisor, the people that sit on my panel, spent a lot of time talking with them and just trying to get their thoughts on the different things that we were trying to do. And then probably is just understand the instrumentation you're using and its limitations.
And along with that, I mean, soil science is fun for the soil scientists.
Yeah.
But for the broader audience, what were some of the potential real world applications for some of the work that you were doing or the research that you were doing?
Yeah, that's great. Well, actually, I'll go back to that undergraduate project first. Some of the work that we've done with that has actually had a really big impact on our hydrology models. Mm-hmm. So a good example is actually at that same facility that I did my graduate research work. We did some work as an undergrad, and we had these watersheds where we actually were measuring all the runoff. Mm-hmm. And we had one big storm event that came through at one time, and I think it dumped like 2 inches of rain in like 2 hours. So a pretty heavy rainfall event. No runoff was measured. Oh, none really? Whatsoever, even at the highest, at that high of intensity. But if you looked at the water content, the antecedent soil moisture before the event, you can tell that it was dry, so that meant there was a lot of cracks open. Mm-hmm, mm-hmm. And essentially what happened is all that water that came in just ran down those cracks. Wow. And so what that work has allowed us to do is actually then better improve the hydrology models that will help us better predict things like, okay, this rainstorm event coming through, what is our risk of flood? What is our risk of erosion? Like, what are the things that real world implications of this type of stuff are? Flooding, erosion, nutrient loss, all these things. And so it's helped us improve models, and that work is being used now in, I believe the model is the SWOT analysis. It's helping researchers now better model hydrology. So that's really cool. And then in our graduate research that I did, this is before soil health was a big thing. Mm-hmm. And it was, trying to quantify the impacts of land use on soil hydraulic properties and just soil properties in general. Mm-hmm. One of the things that we saw was the field that had the best ability to kind of take all that water and infiltrate it and had the best hydraulic properties. If we were to say, all right, our goal is we want the soil to retain a lot of water, to be able to hold it and have it there to be plant available. Mm-hmm. But we also want it to be able to infiltrate that water during intense storms to reduce runoff, because runoff just leads to a lot of problems. And obviously the thing, you would think about it, but the field that had the best properties was the native prairie. Mm-hmm. And that's because there's grass, there's microbes, everything's happy. Yeah. And so a lot of that preliminary work is essentially is what now is built into soil health in general. And that's just a component of soil health, is understanding these properties and the impacts that our land use and the way we use the soil, the long-term stability of that soil, its long-term producibility. Mm-hmm. And now finally people are starting to think about this in terms of, okay, how can we better manage our soils to improve these properties, but also improve the long-term productivity of the soil, that it's actually going to stay there for future generations. Right. So
when it comes to land use, are you looking at land use when it comes to farming, ranching, forage, suburban, development, all of the above, and then some?
Yeah. So that's, the main focus at that time was we're just looking at your basic typical land uses: improved pasture, which is just your typical grazing, and then native prairie, which just means it's native grasses. There's really no grazing happening or anything like that. And then conventional tillage. Yeah. As we go further and dig deeper into it, we didn't do a lot of this work, but I did help the NRCS do some measurements at some different sites when they were doing soil surveys, and got the opportunity to measure in some fields that were actually in more improved management practices, but that were still being grown on. So strip tillage or no tillage fields. And what was really interesting is those two fields, especially the strip tillage field, actually had really good, really high hydraulic conductivity. So overall good hydraulic properties. Now, none of that made it into my thesis because that wasn't the focus of what we were doing. And that's more so what people are looking at now in a lot of these soil health research projects. Right. But yeah, what we saw was even in conventional agriculture, if you can improve the way you're doing things, whether it's no tillage or strip tillage or cover cropping or whatever, you can improve those hydraulic properties. So that's more of an extension of what we were looking at.
Got it. So You talked about issues with variability. You talked about being able to take a lot of measurements, planning ahead. Were there any other, like issues or problems or challenges that popped up that maybe you hadn't foreseen in your research?
The thing that really cropped up was just the amount of time it took to make the measurements and just how much labor that actually took. Fortunately, I had some really great that really helped me a lot with my research. But I spent hours out in the field. I even had my wife out helping make measurements.
Right.
So it was all hands on deck to get those measurements, and it just took a lot of time. I mean, we spent countless hours in the field. So that was probably one of the biggest challenges. And then also just getting the equipment to work right. I mean, we were working with, because we were trying to make so many measurements, we built a system to work semi-automatically to automate the measurements so we could run 3 rings at the same time with 2 people, which at that time there wasn't a lot of people doing that. So we just spent a lot of time in the field, and in the Texas heat, that can be rough. So yeah. And actually another interesting one was actually where you get your water source. That, when you think about measuring soil hydraulic properties, people don't always think about soil chemistry or the chemistry of the water that they use.
Right.
And so we had to get our water source from the site that's local, that's best representative of the water that's going into the field. And we also went through a lot of water sometimes. Like we went through, at one point in time, we went through 1,000 gallons in one day doing measurements, which is a lot of water. So I just, those are the challenges that you don't maybe think of at the very beginning, but you definitely encounter as you're going through your project.
Right. So there's also a rumor floating around that you were out in the field so often that Google Maps has a picture of you doing your research in the field. Is that true?
That is true. Yeah, actually, it's really funny. I was looking for an aerial image of our site to use for a presentation. And so I start looking around, and I start pulling up an image, and then I pull up an image of our field, and I see a speck in the field. I'm like, oh, that's interesting. And I was like, I don't remember that being there. And so I zoom in closer, and I start looking at it like, oh, wait, that's me. That's our trailer. There's our truck. There's the rings in the field. You can see all that. And there's probably us sitting just sweating. Some of those were good days, and some of those were hard days.
From all of that time-intensive work, kind of developed the beginnings of your thoughts and ideas towards what has become the SATURO here at Meter. So can you kind of shift gears and tell us a little bit about how that came to be and how it moved from kind of idea to finished product?
Well, fortunately, after I finished my graduate studies, I was able to get a job doing something that I really enjoyed, which was the product development side of it. I enjoyed as a grad student developing that system and making it work. And when I came to Decagon at the time and now Meter, I started talking with Galen. And, when I first started working here, we started talking like, oh, what are some of the things that you worked on? And, talked about measuring soil hydraulic property. And we're like, man, we've got to be able to do that better. We've got to be able to come up with a better way to do that. And so Galen started thinking and doing a bunch of research, and my goal was always like, how can we make this better? And that's the goal in anything that we do here, is how can we make the measurement better? How can we make it easier? How can we make it more accurate? What are the ways we can make it better? And so we started talking with Galen and just started brainstorming on ideas and we did a bunch of literature research and saying like, okay, what's the stuff that's out there? What are the methods that people are using? And went through a couple of different options, but really settled in on what is known as the dual head approach. And that approach solves a lot of the pain points with your typical double ring infiltrometer or your traditional single ring infiltrometer use, because it gets rid of it simplifies a lot of things. One, we only have to use one ring, so it's less water that we have to use for the measurement. And two, it because of that dual head approach, it eliminates the guess factor. So typically with most either the single ring or double ring method, to correct for that 3-dimensional flow, we have to guess at our soil properties. And it's great if you guess it right. Then you go and look at a table and like, okay, this is my alpha value. This is what I'm going to plug into the equation to correct for the sorptivity and to correct for that 3-dimensional flow. But again, that's a guess. And the dual head method actually allows you to get at that parameter, allows you to actually measure what that parameter should be. And so you're not guessing at things anymore. And so we actually talked with John Norman, one of Galen's old colleagues from the University of Wisconsin. And he had done a bunch of work with this approach and showed us some of his measurements and what he did, and talked through like, okay, how are you doing this? How come And at the time, what they were doing is they were adding water to get to that second height, and then they were letting it drain, and then they were running it at the lower pressure head, and then they would have to manually add water again. We're like, okay, I like the approach. The data is amazing. Well, how can we make this process better? And so a lot of that led into okay, well, let's get rid of the need to add water. Let's just use air pressure and simulate that hydrostatic pressure head. And then we'll just maintain a constant level always. And that completely simplifies everything. You don't have to really monitor how much water is being added. As long as you make sure your water supply is there, then you're good. And it just simplified so many things about the measurement. And it probably would have reduced my water usage to, I don't know, maybe 15% of what we were originally using, just because it was a smaller area, and it just, I mean, I've never ran the numbers on how much water I actually used, but if I were to take a stab, 300 measurements, probably somewhere around 25 to 30,000 gallons of water. That's a lot of water. It's actually, now this is the first time I've actually thought about that.
That's a lot of water.
So, I don't know. So that's a lot of that is what led into the thought process. Like, okay, let's just make this measurement better, and let's come up with an approach to do it. So
a lot less water, a lot less babysitting as well, a lot less hard labor. So how long did that process take, just from first idea to the end, and how many iterations did it go through?
So it actually went through a few iterations. We probably had 2 early prototypes, and have worked with several interns to actually run these measurements. Fortunately, we were able to convince some of those interns to go back to grad school, and then they came back and worked for us now as engineers, which is great. But it probably, from the time I started here, it took probably 6 months to kind of just think of the idea. And then we probably spent a good 2 years iterating on it, and went through, I'm pretty sure 3 different iterations, and then kind of came down to the final design, which is now the SATURO, after about that 3-year period. And then it probably took another year or 2 years and 6 months. So then it probably took another year to finish the development and actually get it released. And so I believe we released the SATURO or the dual head at the time in 2015, if I'm remembering that correctly. So that fits right with that timeline. But it took a while. Got to play with a lot of different things. We broke a lot of things. I was going to say, So, I mean, during that, those years long development process, what were some of the other, challenges, speed bumps, roadblocks that you came up against? And how'd you deal with those? Actually, the biggest roadblock was the math.
Really?
We really had to think through the theory of how we were going to put this together and make it work. And so Galen took, this is the beauty of Galen. Right. I mean, he can sit and look through different equations, looked at the old Reynolds and Elric dual head equations, and then looked at some of the other work being done by John Nemo, and looked at the math and was like, okay, well, I think if we combine these 2 things, we can actually simplify the math and actually make it work and simplify the process. And so it's some of this is written up in the manual. It's on the theory section of like what we pulled together. Right. But really, I mean, what Galen did there was really cool, and how he combined those methods. And outside of that, it was probably finding a pump that could manage. So the problem with hydraulic conductivity is it's a huge range. You can have something that's infiltrating at 0.5 centimeters an hour to 130 centimeters an hour. And to get a pump that can manage that type of variability was actually harder than I would have thought. And so, just sourcing the right parts and then just validating it. And that took a lot of time to just actually make sure what we were doing was working as we expected.
Any other funny stories along the way?
Gosh, we worked with a couple interns on this project. One of them, if you say their name in the company, Kalen Wacker, everybody knows him, and he's got the most unique laugh. But it wasn't the stories about the instrument. It was actually the people that we got to work with on the project. So it was really great. Matt Klutenberg, who's now a mechanical engineer, also worked on that project. His dad is Gerard Klutenberg, who's a soil physicist. So it was really cool to connect with those people. It's really neat to work with another soil scientist's son and kind of bring that together.
Do you see improvements there that, like, in the next generations of SATURO, you know, what could be improved upon?
You know, this is funny, but this is probably, there's two things that I'm really proud of about this device. One, the most exciting thing I see is when I look on, for example, I get on Twitter and I see people posting like, we're having so much fun using this device, and it just makes things so much better. And I'm like, wow, that's so cool to see that something I worked on and helped develop is making somebody's research better. They're enjoying it. They're actually having fun with it. Right.
They're calling it a toy instead of a tool, or,
exactly.
I have to use this. It's, I get to use this. How fun is that?
That's exactly right. And I never probably would have thought that I would, like, that's hopefully the type of impact I can have on the field is by helping develop instruments that people use and go out and solve big problems. And, you know, from there, you know, it's super awesome to see people posting on Twitter that they love using it, but also it's now been adopted by the NRCS. And I remember going out with those guys and they hated making hydraulic conductivity measurements. They're like, oh, this takes so much time and I've got all these other things to do. And so now they have a product and a tool that they can just set up and let it run, and then they go do all their survey stuff. And so it's so cool to, like, just tie things back around with where I started, because my graduate research was funded by the NRCS, spent time working with them on measurements, and now we have a tool that they can use and it works better for them. It's easier for them to use. They're happy to use it. And I remember going down and doing some trainings with them on it, and they're just like, oh, this is so awesome. Like that, having that type of impact in the field, and also in the soil health stuff, like seeing it being used by the Soil Health Institute to do their North American research project. Like, it's cool to know that, you know, although I'm not in traditional academia anymore, the work that I'm doing is still impacting that and having a bigger impact on the field. Right. So that's the cool part.
That's awesome. So how soon until SATURO is going to be industry standard?
I hope that it's starting to become the industry standard in the soil science world. We're seeing it used a lot more heavily, and it's being referenced in, you know, as a tier 1 measurement for soil health properties. So I think it's getting there. But the other world is the engineering world, and that's much more challenging because they're based on standards. And changing standards is worse than trying to pull teeth. So I hope that we can eventually get those things changed, because I think this is a tool. I mean, we talk with engineers that are able to use it and they love it. So hopefully we can get those standards changed and get this more out there for engineers as well, and hopefully help make their lives a little bit easier.
So coming back full circle, we've kind of specifically talked about SATURO and your work here at Meter. Coming back to you know, soil science or soil infiltration research in general, how do you see the field is right now, and do you see that there's still room for growth for future discoveries, or is there, you know, things that you would like to see changed or improved in the field as a whole?
In any scientific field, there's always going to be room for growth and room for better understanding. As tools become more sophisticated and we have more technology out there, like, really what we're doing is taking technology that's built for another industry and finding ways to integrate it into the soil science world. You know, finding ways to more rapidly characterize soil properties in general, not just hydraulic properties. Like, that's a part of it. And hopefully we can continue to make strides in that area, make it easier to measure saturated hydraulic conductivity, maybe make it easier to measure unsaturated hydraulic conductivity in the field, and measure at depth and characterize actually how it's changing throughout the profile. Because, you know, as you measure at the surface, that's just one part. There's a lot more happening down below that we need to understand. Really, the challenge is just there's so much to measure with rapid characterization of these properties. Like, there's a lot of work being done with Viz and AR to try and characterize and build models to characterize these properties, but that's just a piece of it, and it has its challenges as well. I don't really know what the next one's going to be. We have to just keep getting better and find new ways to tie in what's happening, even with remote sensing stuff. Like, remote sensing is a key part because it helps us tie these point scale measurements with the broader field scale of what's happening, and kind of have to wait and see where the field goes and you know, where we go as a company as well, and trying to help make those measurements.
Any final thoughts or comments you'd like to share before we close here?
For me, really had the fortune of getting to work with some great scientists within the company and as a researcher as well at the university. The challenge we have is getting more people interested in the field and keeping that growth going, because I think we have a really important field. Soil science and just, agricultural research in general is key for the stuff that we're trying to do. From there, I think the education on how land use and how the decisions we make to manage property or manage our land and our soil can have a larger impact down the road. So we have to be less short-sighted and think in the longer term. Those are the things that I think are super important as we continue to grow and evolve and try and make things a little bit better. Mm-hmm. Those are the challenges.
Definitely. All right. Well, our time is up. Thank you, Leo, for joining us today and sharing your passion and your projects with us. For you in the audience, if you have any questions, feel free to contact us at metergroup.com. Or you can reach out on Twitter at meter_ENV. Also, you can view the full transcript of today's episode in the podcast description. And that's it for now. Stay safe. Thanks again, Leo. And we'll catch you next time on We Measure the World.